Hello, welcome to this lecture video. So I'm teacher Melay, and today we are going to talk about age-adjusted mortality rates. So what is age-adjusted mortality rates? Mortality rates can be used to compare the rates in one area with the rates in another area or to compare rates over time. So however, because of mortality rates obviously increased with age, a higher mortality rate among one population than among other might simply reflect the fact that the first population is older than the second. So we use age-adjusted mortality rate for us to eliminate the distortion caused by the different underlying age distribution. So we actually can compare two different locations. For example, if we are going to compute for age-adjusted or age-standardized mortality rates and not just simply the age mortality rate. So here, we have the computation of the age mortality rate or death rate. And for us to compute for this, if you still recall in our previous video, what we need is the number of death and the number of population that belong to that particular rate. So just to illustrate how it is done, so let us consider the calculator. So how to show that. So for example here, so let us consider less than 1. So this value. So how did we obtain 553.4? So to compute for that, we will simply divide 55 over 9,938 is equal to this value. However, it's noted here that it is per 100,000. So which means we need to multiply it by 100,000 and the result is 553.43 is the death rate for age group less than 1. While if we are going also to compute for age 1 to 4, so to get this value, 331.2, so to compute for this, we will also divide 12, the number of deaths that belong to age group 1 to 4, all over the population of age 1 to 4, which is 38,503. So multiplied again by 100,000. So the result is 31.166 or simply 31.2 in our table. So if we are going to continue with this, we can obtain the values here by simply dividing the deaths and the population indicated in the identified age groups multiplied by 100,000. So in the case also of Florida, so to compute also for the death rate on the last column, so it is also 1,548 all over 205,579 multiplied by 100,000. So if we are going to compute for that, for all the number of deaths here and over and the population for each of the age group, you can obtain these values on the last column. Okay, so now if you reach the total, so this is the total. So for you also to compute for the total, so you of course have to add the total population. So this is actually not the total population. So let us recompute for this value. So using our calculator, so 9,938 plus 38,503 plus 50,400 plus 57,216 plus 56,634 plus 42,929 plus 84,102 plus 107,305 plus 103,039 plus 52,543 plus 24,096 plus 11,784 and the last one plus 3,117 for a total of 641,616. So let us place it here. This is this value here is 641,616. Okay, so let us just double check the values. 9938, 38,503, 5040, 57. Or maybe we can proceed by dividing now the value. So this is the total also if you add the total debt. So it's 3,030. 3,030 all over the population, 641,616. It is 47.2 because if you will multiply this by 100,000, it is 472.2. So this is the value. So the same procedure is done on the other side. It is also adding all the total number of deaths here and also for the population. So if you divide this, you will obtain 1,005.7. As you can see in the value here, so the value of the Florida is higher than the death rate of Alaska. And by also considering the age-adjusted rate now, this is another computation, and the computed value for Alaska is 794.1, while the computed for Florida is 787.7. So in computing for the age-adjusted rate, we have to consider the standard weighted values. And uh, just to show you an example of that, so we have here, let us consider this. So this is an example also of the computation of age-adjusted rate, but for particular cases. So it's a diabetes case of diabetes mellitus. So as you can see here, when we computed for the value of our death rate, so this is the death rate for age specific death rate, because of course we have here under 1 year old, 1 to 4 years old, and so on and so forth. So the formula is the same. This is 0 over 350. Of course, you will get 0. And on this side, if you will also compute 1 over 1,400 4,269, you will get 23.43. But what we are trying to say here is that you have also to compute for or to obtain the value of the standard population weight. And in the case of this example, these are the values of standard population weight. So let us just emphasize these values. So these values are, what I'm talking about is the values here. So you need that. So if you have that value, what you need to do is just to multiply it here, just like in our data. 0 times this value. So it is 0. 0 times the value of the 2,000 standard population weight. So this is the US standard population weight. It is also 0. But for this value, so let us just verify using our calculator. So let us compute 23.43 over rather multiplication. So this is multiplication, 23.43 multiplied by 0.162613, and you will get 3.81038. So this value here. So you just need to multiply, and then after that, add the result here. So after obtaining that value, you need to add the result of the product of age specific rate multiplied to the US 2000 standard population weight. So if we will add this, so it's 3.81038 plus 1.45791 plus 12.21719 plus 6.584872 plus 2.938097 to get a total of 27.008, or this is 22.01. And this is now the computation of the age-adjusted rate for diabetes mellitus in Sierra Country, New Mexico. So if we have the data for the US 2000 standard population weight, so it is also possible for us to compute for the values of what we are looking for. So for us to compute for the cross product or the product of age-specific rate with US 2000 standard population weight. So for example, so if we will consider here, so I actually search for a value, and we have here the following values. However, as much as I want to try to recompute the values in our table, so let's go back to our table. So let us go back to our table. So as much as we want to compute for the values here, it doesn't match. So just like for instance, let's go back here. We have less than 1, we can compute for that value. So it is here, however, it's 0.013818 for 1 year old, 2 to 4 years old. However, in our table, so what I found is only 1 year old, 2 to 4 years old, 5 years old. But what we need is the standard or the adjusted weight for 1 to 4 years old, 5 to 9 years old, and it's not the same in this table. But you can still search for that value and recompute it so that you can recheck if it will be equal to 794.1. So you will just compute for, or rather you just need the data for adjusted weight for you to compute for the age adjusted rate. Okay, so let us move to another table. So aside from that, we also have here the computation of death to case ratio. So what's the formula for death to case ratio? This is the number of deaths attributed to a particular disease during a specified period over the number of new cases of the disease identified during this specified period times 10 all over, or rather 10 raised to N. So given this example, so between 1940 to 1949, so there is a total of 143,497 incident cases of diphtheria. So during the same decade, 11,228 deaths were attributed to diphtheria. So how to calculate the death to case ratio? So you just, of course, need the number of cases. So the number of cases, death cases is 11,228, and the total number of incident is 143,497. So you will get a value of 0.0783. But just like with all other examples and also the example provided on our table above. So let's go back to the table. So we can also compute for death rate multiplied by 100,000. So in the case of our example here, if we are going to multiply it by 100, it means that the death rate, death to case ratio is 7.83 per 100 cases. So this is all for this video. Thank you for watching and thank you for listening.